Hello, everyone. My name is Adam, and I am your AI tutor. In this first episode on AI engineering fundamentals, I want to give a perspective on prompt design that I've gained with over 6 years of AI experience and a PhD in electrical engineering. This episode is crucial for those of you interested in designing agentic systems, RAG pipelines, or just want to reduce the chance of hallucinations when using large language models. Today, we are going to understand why prompting works, how it works, and how to design prompts that give you predictable, controllable outputs. And if you like technical content and would like to help grow a community around learning topics in AI and engineering, please consider joining the Discord link below. This is a very exciting section. Here, we're going to look at what are large language models actually doing, and from that, we will work backwards to design better prompts. Let's start with a small example that you've probably heard of. Given the phrase, the cow jumped over the, even before I say anything, your brain is proposing a likely word. Maybe moon, maybe fence. LLMs do something very similar. They estimate the probability of every possible next word and select the most likely continuation. But behind the scenes, a model begins with a massive vocabulary. Tens or even hundreds of thousands of words, subwords, and unique characters called tokens. A bad prompt makes these equally likely, shown by the uniform distribution on the right. We can picture this distribution across the model's vocabulary as being a random word guessing machine. Our job as AI engineers is to reduce the randomness associated with guessing the next word. Here, we can view good prompting as shaping this distribution across the model's vocabulary in a way that increases the likelihood that it will select the correct next token. In this example, we can see the model is most likely to select moon, but there is still a chance that it could select fence as its completion of the sentence. So here's the first discussion question. You are using a large language model with an initial uniform probability distribution across its entire vocabulary. You are working on a document classification problem to aid business analysts in identifying high priority and low priority input from news outlets and internal repositories. My question for you is, what is the length of the language model's vocabulary? When you use a large language model, you're working with a very large vocabulary of tokens. Here's the key takeaway. A large vocabulary can give you flexibility, but it also creates uncertainty. Because the model has many possible next outputs, prompt engineering helps reduce that uncertainty so the model becomes more accurate. Let's look at an example. If I ask, what is Anne's favorite animal? The model has almost no context, and the space of possible answers is massive. For illustration, I've highlighted 4 possible answers, and the model would have no way of knowing this. It would be a complete guess, again, showing the uniform probability distribution. But if I add context like, I always see Anne wearing dog earrings and animal scrubs, now the model's probability distribution collapses. It becomes far more likely to choose dog. This is what prompt engineering does. It reduces variance. It increases the probability that the model gives you the answer you want. Now that we have looked at what the objective of prompt engineering is, we will explore the data types that large language models are trained on. This will help us develop additional tools for communicating our intent and increasing the probability that our AI selects the correct next word. Large language models go through a process called pre-training, where they are exposed to large amounts of data, highlighted here. This data shapes the model's understanding of the world and gives us patterns to align our intent with the output we want. Moving forward, I want you to think about matching your prompt to more closely align with these data types. Here are examples of data types we primarily rely on: JSON, Markdown, and XML. Each of these offered structures to help elicit a response from our model. For example, a combination of Markdown and JSON can be used to provide instruction and enforce a data type that can be read directly into your programming language of choice. Back to our earlier question, what do we want the vocabulary size to be? In this task, we would ideally have 2 choices: high priority and low priority. which is the case in most tasks. We want a smaller, more effective vocabulary, not by modifying the model directly, but by designing prompts that restrict the universe of valid outputs. So how do we approximate a smaller vocabulary? We do it by providing context, instructions, constraints, and structure in the form of a prompt. Now that we have a background in what the objective of prompting is and where the data comes from, we can begin learning the core techniques to build high-performance prompts. The first technique we cover is what we call zero-shot prompting, or prompting that is directly asking a model to perform a task with no context or examples on how to respond. Tying this back to what we have already learned, this creates a more equally distributed chance of selecting random words. This technique is best for exploration of topics and with problems that don't require strict adherence to structure. Building on zero-shot prompting, we add role adoption. This can be thought of as increasing the likelihood of words being used that an expert in a field would use. Where the model is given an identity, but the instruction is unclear. It knows how to behave vaguely, but it still doesn't know what we need. This leads to verbose or misaligned outputs. However, having the model adopt the role of a helpful assistant helped reduce the variance of the output, which is shown by providing a more concise answer. Now, we look at a better implementation of role adoption. Here, we have the model adopt the specific identity of an assistant that does one of three things. Responds with positive, negative, or neutral, depending on the sentiment of a review. Traditionally, AI would require us to train a specific model whose only job was performing this task, which is why the techniques we are covering are so powerful. With this, we have provided guidance on our expectation. Now the model knows ambiguous classifications are not useful and will accommodate our requirements by classifying a review into one of the classes we have defined. Now we look at a technique called single-shot prompting, which is where we provide an example of input and output relationships. In this example, we use a combination of Markdown and XML to communicate the role, the example, and what to review. We see a significant reduction in how verbose the model is. This allows for an easily interpretable and more parsable output that we can handle programmatically. Now, we are about to put everything together in one final example. The technique we are about to cover is called few-shot prompting, and it excels at guiding models to strictly adhere to structures you impose on your specific problem. The problem we are about to cover is creating a low-variance model that classifies reviews and outputs them in a consistent format. To start, we leverage Markdown to clearly specify the role the model should take. We give it the identity of a helpful assistant that labels short product reviews as positive, negative, or neutral. Then, we provide a section using Markdown for instruction. The instruction section imposes further constraints, biasing the output to better adhere to our desired format. Now, we can start providing examples for our model to better understand how to respond. We will denote this with Markdown. Here, we give the first single-shot example using XML tags. Then finally, we include multiple input-output relationships to complete our few-shot prompting example. So to wrap it up, these models are next word guessing machines that learn from patterns in data, and prompt engineering is about leveraging those patterns. Our goal is to program probabilistic systems using natural language. And before we go, if you want to dive deeper, share ideas, give feedback, or follow along with the rest of the series, join our Discord community using the link below. If you found this helpful, don't forget to like the video and subscribe so you won't miss the next part of the series.